So welcome everybody. We continue with the QGASLAB string seminars. It's a great pleasure to have Johanna Erdmenger from the University of Würzburg talking to us today about their recent paper on complexity for chaotic systems and ADS-CFT. Johanna?
Yes, thanks a lot, Jeff. So thanks a lot again for this very kind introduction, and I'm very happy that you have me. And I'm also looking forward to coming to Cape Town in person again in a not too distant future. I think it's almost 10 years ago since I came to see you.
That's right.
Yeah, I have lovely memories of that. And of course, everybody's also very welcome to Würzburg if we can arrange that. So let me know. All right, so today I'm going to talk about complexity, and so most of the talk will be devoted to a recent paper about complexity for chaotic systems. And but towards the end, I also mentioned some work because my area of research obviously is holography most of the time. So I also mentioned some other recent developments related to ADS-CFT. And of course, one big question will be if we can, in the future, have a link between the two. But today, at least the two parts of the talk are a little bit disjoint. So here you can see the castle overlooking the River Main in Würzburg. So Würzburg used to have a Prince Bishop for 1,000 years until 1803, when Napoleon ended this reign of the Prince Bishop, and Würzburg was given to Bavaria, essentially. And so this is a view which I have from the balcony of my small apartment, so it's actually quite lovely. And it's also in summertime, so you can see the sun setting here. Anyway, so briefly, also let me mention the funding, which comes from the so-called Excellence Cluster, which is a federal science program here in Germany. And so it's a joint enterprise of mostly condensed matter physicists in Würzburg and Dresden. And they provide substantial funding here for also this project. All right, so I will first remind you briefly about what quantum computational complexity is. And then, as I said, I will mostly turn to Krylov complexity for chaotic systems. And then towards the end, I mention some aspects of complexity for two-dimensional CFTs and their gravity dual. All right, just to bring everybody on the same page, let me give a brief review of what complexity is. So essentially, the starting point is to look at a particular Hilbert space. And so I should also say, originally, this is a concept which really comes from more experimentally oriented many-body physics. And so we can first think of a finite dimension Hilbert space where we have a particular reference state and then a set of unitary operators, which are called the gates. And then the complexity of a given state is given by the minimal number of gates required to map this reference states to the final state up to a given tolerance. So, and the sentence here is summarized in this equation that you see here. And so this is a well-defined concept for pure state in finite dimensional Hilbert spaces. And however, for infinite dimensional Hilbert spaces as required for quantum field theories, there's actually no standard definition. And this is one of the obstacles for actually writing down a gravity dual of complexity. I mean, there are some proposals, but to actually have a proof, or I mean, a very good substantiation of this claim, there's open questions which arise from this fact that we are dealing with infinite dimensional Hilbert spaces for quantum field theory, so it's not quite clear to how to define the states and also these gates in that case. Okay, so and there has been a lot of interest in these topics from ADS-CFT in the last 10 years, and that goes back to some papers by Lenny Susskind. So he considered the evolution of two copies of a CFT that are initially entangled in the thermal field double state. So essentially what you have, there's an eternal black hole depicted here essentially in ADS2 space, where we have time going this direction, and this is the radial direction. And so this is the horizon, and we have a left and a right CFT if we consider a global space. And Susskind realized that entanglement entropy is not really quite enough to describe the late time evolution of quantum black holes. And so the complexity would be an additional feature borrowed from quantum information theory that we can use to describe the late time evolution of black holes. And so he essentially made two different conjectures. One, that the complexity of the dual quantum field theory corresponds to the volume here. So the volume in this picture is essentially the length of these geodesics, and so which correspond to the Einstein-Rosen bridges, if you want. And then another proposal is that the complexity is equal to the action on a Wheeler-DeWitt patch, which you can see here. And the reason why this is supposedly a good proposal for the holographic dual of complexity is that both these quantities evolve linearly with time. And this is also something that complexity does, because if you say every step of applying a gate is done in one time step, then obviously you have a linear time evolution, because if you apply 3 gates, then it takes 3 times as long, and so on. And so of course, these proposals are beautiful, but it's an entire program in ADS-CFT to actually find some substantiation of this and make it very precise at the level of the holographic dictionary. And this is what I'm going to talk about towards the end of this seminar.
Sorry.
Yes.
I have a question.
Yes, sure, go ahead.
So Susskind and Brown and these guys didn't really specify what complexity was dual to volume or to action, right? There's just this notion at that stage that it was complexity, and I guess for the most part they meant Nielsen complexity, right?
Yes.
Okay.
Yeah. Okay. So I think, well, probably yes, and I think that's one of the open questions that needs to be addressed. I mean, if we really want a well-defined entry in the holographic dictionary between complexity in field theory and gravity, then really what is missing is a unique or well-defined notion of complexity in quantum field theory. And so that's really still an open question, I think, to really have a kind of very substantiated definition of complexity on the field theory side. And maybe I can say a little bit about this towards the end. But so the Krylov complexity, which I mentioned in the meantime, of course, also has some appealing features in this directions, but still there's also no holographic dual of Krylov complexity yet. But maybe in the future there will actually be. I think many people are working on this right now. Yeah, but it's exactly true. I mean, so this idea that somehow this quantum information concept of complexity is related to a geometric object, that goes back to, I think, this paper of Michael Nielsen, which was mentioned by Jeff right now. So Nielsen is actually a mathematician in quantum information science, and so he considered finite dimensional Hilbert spaces. But so he was the first to provide a geometric realization of this concept of complexity. And so here there's just a brief summary. Oh, it looks like some parts of the equation were missing there. I'm sorry. Anyway, so to estimate the computational cost of quantum circuits, one can look at a type of gates which takes this form. So this is a unitary transformation, and here we have a particular Hamiltonian, and this is the path order product. Okay, so this is a quantum circuit that we can define, and Nielsen considered that in the concept of group theory. For instance, if you have a collection of 10 spins and each of them can point up and down, then for each of these spins you have an SU2 manifold, and they create then an SU2 to the n manifold. And so he was establishing this complexity measure based on metrics on this group manifold. And in fact, what he said is that complexity should be, I mean, I think at first he gave an upper bound, but then actually tighten this proof to actually make it an equality, is that the complexity would then correspond to the length of the shortest geodesic between some initial value of this unitary transformation and the one corresponds to the final time, to the state at some given time that you would like to consider. And then the complexity would look like this, and somehow, for some reason, some equations went missing here. I'm sorry, I think that's when I exported Keynote to PDF, partially things disappeared. And so this function f is a so-called cost function that you have to define. So what is the cost of taking a particular step in this manifold? And that enters the complexity in this way given here. Okay, now let's take a slightly different route at the beginning. And I think this is a topic which is also very dear to Jeff, because Jeff and your group, and probably also your co-authors are also in the audience here right now. So you also had some very nice papers on Krylov complexity. And so that's also what I'm going to talk about most of the talk. So this is really about mostly quantum mechanics systems and quantum dynamics and random matrix theory. However, of course, I wanted to mention these holographic complexity proposals at the beginning, because certainly for me, this is the most motivation to look at the Krylov complexity as well, and it's still an open question, but of course something I think which will be addressed pretty soon, how to find a gravity dual of this. So what is actually Krylov complexity? Or I guess the people who worked on it before, they know, but let me just state it. So Krylov complexity measures the spread of a time evolving state in a Hilbert space. Right. Okay, so there's actually different versions of Krylov complexity. There's the operator and the state version. I will refer to both of these in a few minutes. And so what I'm mentioning here in this first line is actually already the state version that we'll mostly be dealing during this talk. And so essentially, this complexity has some very important nice features which make it very convenient for many applications, is that, for instance, for maximally entangled states, it depends only on the spectrum. This I will also show to you later during the talk. And in particular, it's independent of the choice of fundamental gates. And that makes it very appealing for trying to find a gravity dual of this, because that's just one of the questions which in the CFT are very hard to address. So what is the choices you should make in a quantum field theory to define the gates, where if the theory has a Lie group symmetry, then of course, in principle, there's an infinite amount of gates, but of course, if you have infinitely many gates, the concept of a complexity becomes a little trivial, because then with just one step, you would reach any state in the Hilbert space. And of course, that's not what's meant. You have to have a predefined set of gates for this standard quantum computational complexity that I mentioned before. However, this Krylov complexity is actually independent of this choice of fundamental gates, and that makes it very appealing. And now in the context of quantum dynamics, it's very relevant for analyzing chaotic behavior and also for probing quantum chaos, as I will explain to you. All right, so let me just mention that now this largest part of the talk, which will be about this Krylov complexity, is based on this paper, Universal Dynamics from Krylov Space. And so this was written in collaboration with our postdoc, Zhou Xian, and also Shaokai Jian, who is, an assistant professor at Tulane University in the US. And Zhou really he's in the audience here, and he's the one who initiated this project, and he did all of the calculations essentially, and I'm very impressed with his work, and so I'm very happy that he's able to join today. So this was this paper in March, and I think that prompted Jeff to invite me for this talk, which is very nice. Okay, and then towards the end, when I talk a little bit about some this more standard quantum computational complexity, There's a paper written by my students, Marius Gerbersang, who is now a postdoc in Brussels, and Annalena Weigel, who is completing her PhD here now, and Michael Heller, who is a professor at Ghent University in Belgium. And so I should thank all of these collaborators for the very pleasant collaborations, in fact. Okay, so after this introduction, let's now turn to the creed of complexity, and let me describe to you the outset of this work and also the results that we obtained. Okay, so let me briefly explain what creed of complexity is. And so at the beginning, I'm going to follow this paper here from people working in many-body theory. And so as I mentioned already, the important feature of creed of complexity that is in some sense basis independent and independent of the choice of gates. And as I mentioned before, also there's an operator and a state version of this complexity, although they're very closely related to each other. So on this slide, at the beginning, I'm mostly talking about the operator complexity, and you can think of this complexity being a measure on the state spanned by the operators in a given quantum theory. But of course, very equivalently, you can also consider the state complexity where these operators act on Hilbert space, and then talk about this complexity in this Hilbert space. Okay, so the important features is that the operators evolve under the action of the so-called Liouvillean operator, curly L, which is essentially the application of a commutator with the Hamiltonian. And so the observable of interest is the so-called autocorrelation function. So where we start with one state here and then apply a time evolution involving this operator, and until we reach at some later time this operator at a later time. Okay, and then to actually compute this, there's the so-called Langtos algorithm, which iteratively computes tridiagonal representations of a given matrix. So the idea for this creed of complexity is to find the sequence where a certain power, nth power of this operator is applied to O, and then this sequence is orthogonalized with the Gram-Schmidt orthogonalization procedure. So the starting point in the operator space is a particular normalized vector, and so which we can consider to be our ground state, if you want. And then we obtain a sequence of coefficients, the so-called Langtos coefficients, an and bn, and so they are obtained iteratively from this sequence here. So here we have bn, and then here we have the application of this curly L, and so recursively, essentially, we define these coefficients n and bn, where an ensures a proper normalization of the operators. And so also this defines a dimension L of the associated so-called Krylov space. And so the dimension is given by the number of vectors until the next power of this L would actually give you a linearly dependent vector. So that sets the dimension of the space that we get. So the space is this Krylov space, which is spanned by this Krylov basis that we see here. Okay, so now we can write essentially this procedure in terms of an explicit realization in terms of matrices. And so then in particular, we get a matrix which looks like this. And it will be after this orthogonalization procedure, it will be tridiagonal, as you can see here. And so we can also write the basis of this Krylov space by applying a certain polynomial psi n, which depends again on this Liouvillean, to our initial ground state 0. And in fact, from this repeated application, we obtain a recurrence relation, which essentially also amounts to the Schrödinger equation in the system. And so here we see that recursively we can calculate these psi n's in terms of the Langtos coefficients. Okay, so then we can define a state in this Krylov space, which is spanned by the spaces here. And so if we write one particular state in times of the spaces with these coefficients, then the Krylov complexity is actually defined by the ratio of J and P, where J involves the term here with the coefficient n at the front, and P is just essentially a normalization factor that we have here. Okay. All right. So now this concept has some very appealing features, and which I would like to introduce to you now. Now, for this slide, I'm mostly following this paper of Vijay Balasubramanian, Zaputa, Morgan, and Wu from last year. And they investigated the so-called spread complexity. And so the spread complexity measures how a wave function spreads over the Hilbert space. So essentially then what we have is that we start with our initial state. So here we really see that now we work in the state representation of the Krylov complexity. So we consider this as our reference state in the Hilbert space. And then our final state is given by psi tau. So, I mean, it's possible to use both Euclidean and Lorentzian evolution. Most of the time for random matrix models, of course, it's more convenient to do Euclidean calculations, but so this really is a time evolution with this operator L, this Liouvillean, which amounts to this commutator. And now there's one very appealing physical feature or picture that we can have for this, and which already was mentioned in this paper that I mentioned before. So in fact, this time evolution of the state can be mapped to the propagation of a particle along a one-dimensional chain. Okay, so this Krylov complexity actually corresponds to the position of the particle in the chain. So essentially, if you apply this Liouvillean once to your initial state, then you can view this as really having a state in Poisson space where you move by one state, and then if you apply it one more time again, you go to the next element in the chain, and so on. And the position in this chain is determined by the power of L required to reach the final state that you have defined when you started. Okay, so and this picture is actually very appealing, and it gives a very physical realization of this somewhat abstract concept of these power series induced by this Liouvillean. And so in fact, now the idea is really to use this Krylov complexity to quantify how chaotic a system is. And so in a very physical picture, then we imagine that the more a system is chaotic, the more it's entangled and non-local. And so we expect that chaotic dynamics produce very complex states. And of course, the idea is to quantify what we mean by complex. So in fact, what we see is that if we now look at the time dependence of this Krylov complexity, it will actually be exponential in chaotic systems. So then you might want to use this exponential behavior to actually take this as a signal for chaotic behavior. However, indeed, as we found in this paper, and I will discuss a little further along, also at early times, so when we start with applying this L, these integrable systems may have also a similar exponential behavior. So at early times, it's not really so easy to discriminate between chaotic and non-chaotic behavior using the Krylov complexity. Oops. Okay, now let me review. Are there any questions so far? Or I mean, maybe I should ask: are people familiar with what I presented? Or probably yes, because people in Cape Town have been working on this as well, isn't it?
Yeah, I think I think pretty much everybody in the room has heard at least one
Okay,
lecture
so
on kernel
I hope
complexity.
you enjoyed this explanation. Okay.
No, it's great. You can always hear it more.
All right, so let's move on. And so now what we want to do is to make a connection to chaotic systems. And let me review some aspects of chaotic systems, which go back quite a long time to Dyson. And there's also this review by Weidenmüller from '98. And so, in fact, what is a chaotic system? A quantum chaotic system in the general context is to have the time evolution of these systems characterized by the statistics of the energy spectrum. And as was discussed already a long time ago, chaotic systems are characterized by actually two different properties. One of them is so-called level repulsion, which means that energy levels avoid clustering. And on the other hand, there's another feature called spectral rigidity, which means that the number of levels within given energy intervals of given size are roughly constant. And so both features are due to the nature of correlations between the levels in chaotic systems. And they're described by the so-called Wigner-Dyson distribution for random matrix theories. Okay, I should also mention that mostly of the time here in this talk, I'm going to consider Gaussian ensembles, so in random matrix theory as an example. Okay, and also what is very important for what is going to follow is that we will make a lot of use of the so-called spectral form factor, or SFF for short, given here by this label Z. So this quantity Z will actually appear later quite a bit, which essentially, so here we use this complex time coordinate. So T is a kind of Lorentzian time and beta is the inverse temperature. And so this is actually the mod squared of this density matrix or weight factor that we have. And in terms of the energy levels, you can write it in this form here. Okay. And so the spectral form factor is determined by the level statistics and indeed may be used to diagnose chaos. Okay, so let me briefly compare the spectral form factor and Krylov complexity and their time evolution. So this is the generic feature that appears in particular when considering Gaussian unitary ensembles. So this is the typical behavior of the spectral form factor. And so it's characterized as a function of time, and it's characterized by four different regions. So here this is the so-called slope region with, of course, significant fluctuations. Then this is called the dip, and then there's a ramp, and in the end there's a plateau. And so as we will see here also in this talk, this is quite closely related to the time dependence of the Krylov complexity that we see here. And there generically there's a quadratic behavior at the beginning, then there's a linear behavior here, there's a peak when we consider chaotic systems, and then there's a saturation here at the end. Now, generically, it's usual to call everything that happens up to the dip is called the early time behavior, and what happens after the dip is called the late time behavior. And so I will also first consider the linear behavior in the talk first, and sorry, the early time behavior in the beginning of the talk, and the late time behavior later in the talk. And especially also explain the relation between these two things. Okay, so these are generic features and of which we want to make use. So this is for a maximally entangled state, and it's also for the so-called Gaussian unitary ensemble, which is a particular random matrix theory. Okay, so what are the main results of our project I would like to show to you? So on one hand side, we can show that the early time behavior of Krylov complexity is given by a double integral of the spectral form factor. And, oh, there's a typo here. It should be via a generalized Ehrenfest theorem. So this is a typo, it should be theorem, not series, okay. And Ehrenfest theorem, you know from quantum mechanics, I suppose. And so it just means that quantum mechanical systems obey or I should say the expectation values of operators in quantum mechanical systems obey classical equations of motion, essentially. And this we can use in a generalized way also for the Krylov complexity. And that actually gives us a tool to analytically make statements about the Krylov complexity. And the late time behavior is determined by universal properties of the probability given by a wave function in the Krylov space. Okay. So essentially, the new results of the paper is that we can make some analytical statements both about the early and the late time behavior. And so for the early times, this is based on this Ehrenfest theorem. And we can compare them to numerical analyses as well. Okay, so now what I'm going to do is to talk you through the late time and the early time and the late time behavior, and explain what new analytical methods we can use. Okay, so let's begin with the early times. And in fact, for the Krylov state complexity, in that case, as we show in our paper, the Schrödinger equation leads to an Ehrenfest theorem for the Krylov complexity. And by this we mean this relation here. And so really what we have is a classical equation of motion for the expectation value of the Krylov complexity. And so its second time derivative is related to the second moment of K with this Liouville. And so this
sorry, I have a question.
Yeah.
Average of Krylov complexity over what? So Krylov complexity is obtained over a basis already, right? So what does that expectation value there mean?
Yes, exactly. Well, I think that the answer is probably written here at the bottom of the page. Okay, so the question is, I mean, what do I exactly mean by expectation value? Okay, so I think that's explained here. So this equation is a summary of an equation that we obtain by looking at the basis which I discussed before, and actually looking at the Langlois coefficients. Okay, so the way so this is a general form, but this equation is a result of a calculation, and the calculation is performed in such a way that we start with our initial state again, and we consider a final state that takes this form. We look at this complex time coordinate that you see here, and then we calculate the weights which are given by this expression here. And then if you look at our paper, there's a number of steps. And then finally, for this quantity J, which I defined before, let me show it again. Yeah, so this was at the level of the operator complexity, but now we're doing the state complexity. So it depends on this imaginary and real part of the time coordinate. And then if we do this calculation, we get this relation here in terms of the Langlois coefficients. Okay, and then when you arrive at this result, you can actually show that you can sum this up as this relation here. So I hope this answers your question.
Okay, yeah, thank you.
Thanks. Yeah, thanks for asking. Okay, so the logic is really, this is the computation that we perform, and once we have this equation, we actually realize that it can be written in this more general way. Very good. Okay, but so in fact, using this explicit form, we can actually make a lot of statements about the initial behavior of the early time behavior of the Krylov complexity. Okay. And in particular, what we find is that in a particular limit that I'm going to discuss now, and which only applies to the early times, so in the linear growth region, this Ehrenfest theorem, so the Ehrenfest theorem really is this equation here, which just has this nice interpretation that we can write it in this form, actually relates the Krylov complexity and the spectral form factor. So that's I'm going to outline here in this slide. And a very important quantity here is the so-called transition probability, which is this expression here. And so essentially, in this chain picture, so when you map your Krylov complexity to this position in your one-dimensional chain, it's actually the probability of actually going to the next site. Okay. And then another important quantity is the transition probability just of the vacuums or the initial state itself. Okay, so this is I think in this paper by Balasubramanian et al. It's called the survival amplitude. So that's actually S of tau is the number of the expectation value for actually staying in the initial state. Okay, and so if we now consider a maximally entangled state as the reference states in a Gaussian matrix ensemble. So in particular, considering the TFD state that you can see here. So again, I expect that people are familiar with what the TFD state is. So essentially, it's a purified state where you take 2 copies of an initial configuration. Then using this generalized Ehrenfest theorem, we can actually show that for the complexity, we get this expression here. And that actually tells us that the Krylov complexity only depends on the spectrum. So you see that this approach with this generalized Ehrenfest theorem actually allows very useful analytical calculations. Okay, but this we can compare to the numerical analysis. So so here now this is a numerical analysis in the same early time regime, so before the dip. And so here this is a numerical analysis of the Langevin coefficient of a maximally entangled state, evolving with a Liouvillean, which is now this copy because we work with the TFD state. So the Hamiltonian is in the so-called Gaussian unitary ensemble of random matrix theory. And so there's these coefficients an and bn. So the an are the so here n you can see here, and an and bn and plotted on the y-axis, and you see there's a lot of noise in general. But now there's a particular approximation that we can make, and that's actually valid at these early times, is that we can replace the an by just the black line here. And the bn replace them by the square root behavior that you can see here. Okay, so where d is the dimension of the Gaussian unitary ensemble. And so if we replace the explicit value of the Langevin coefficients by these 2 functions, then indeed again, so first of all, we find that the second time, again, using this generalized Ehrenfest theorem, we see that the time derivative of the Krylov complexity will then be approximately equal to this survival amplitude. Okay, S was the survival amplitude here, which you can then write in terms of the spectral form factor. And then, in fact, using this analysis, you can show that in this regime, so when you do these replacements, then the Krylov complexity coincides with the so-called spectral complexity, which is given here. So this is a slightly different concept, which makes use directly of the spectral properties of your chaotic system at hand. Okay, so and just to illustrate the numerical analysis, so you made lots of very beautiful plots, and I show you 2 of them here. So here you can see snapshots of the transition probabilities on this Krylov chain. So essentially, it's the probability of actually hopping to the next site in this chain picture. And so this is here. You can see this. Sorry, I have to. As a function of the Lorentzian time and the Euclidean time, if you want. And so you see that, so L being the dimension of the Krylov space. So at the beginning, the hopping starts at 0 at the beginning, and then these hopping probabilities at a given moment in time. So the blue dot corresponds in early time, and then at later times, we're already much further into this chain. so that you can see very nicely from this picture and here for the Euclidean time. Okay, but the point I want to make is that at early times, it's possible to replace the explicit values, the numerical values of the Langlois coefficients by these functions, a constant and a square root. And if you do that, then we obtain the result which you can see here. Okay. In fact, by using this approximation, we can directly calculate so the Krylov complexity, showing that it's the same as the spectral complexity. And so what we actually see that the growth and saturation of the Krylov complexity are not significantly affected by chaotic behavior. So whether the system is chaotic or not, you would get very, very similar behavior. So at early times, it's not really possible to use Krylov complexity to discriminate between chaotic and non-chaotic behavior. And essentially, the linear growth here at the beginning is determined by the n dependence of the Langlois coefficients. And in fact, then after a while, there's a saturation, which is due to the spectrum discreteness. So this is the picture of drawn by Joyu in this paper that I'm presenting to you. And so for the three different kinds of the Gaussian orthogonal, unitary, and symplectic ensemble, so you can see the solid curves give you the spectral complexity. And and then the Krylov complexity is calculated numerically. So essentially, so the bottom line is the dashed lines. They correspond to the analytic result, I think, and the other ones correspond to the numerical result. And you see at the beginning they coincide very well, but then at late times this approximation of neglecting the noise is no longer valid, and that's why then there's quite a difference between the numerical and the analytical result here. Okay, so so this Ehrenfest theorem is very useful for getting analytical results at early times, but now how about the late times? And so essentially what we find in the paper is that is the following. So let me first recall the general feature. So in generally, it's known that in chaotic systems, the Krylov complexity shows a characteristic peak in saturation structure. And then considering the continuum limit of this one-dimensional change, so this is again an analytical calculation that we performed, we obtain an analytical confirmation of this result. And again, also at this late time, what we can do is to make a connection between or directly relate the Krylov complexity to the transition probability. And in fact, the transition probability exhibits a universal rise slope ramp plateau structure with a very long ramp. I'm going to show you a picture in a minute. And we can also show that it's this long ramp that gives rise to the peak in the Krylov complexity. And here now, unlike for the early time behavior, now at the late times, we can actually distinguish between chaotic and non-chaotic systems using the time dependence of the Krylov complexity, because in non-chaotic system, this long ramp in the transition probability is absent, and this also implies that this characteristic peak in the Krylov complexity is absent. So in this paper by Balasubramaniam et al., which I mentioned before, they already speculated that the peak is actually a signature of chaotic behavior, and then now we were actually able to confirm this conjecture in this paper that I'm presenting to you. Okay, so and this you can see here. So again, there's an analytical approach. And so we can write the Krylov complexity in terms of the transition probability, essentially. So that's given here. So here again, this is the spectral form factor. And here we have the transition probability that appears here. And in these plots, we have on both, so the total field of complexity, and we could look at also for this spectral form factor at the connected part and the complement. So, but I think essentially for us now, what is relevant is this blue curve here, again, with the field of complexity as a function of time. And so in chaotic systems, there's this peak structure, and in non-chaotic spectra, the peak is absent. So, and in this paper, you actually found that both numerically and analytically, we can find this behavior. So we have an analytical result based on this equation, which you see here at the top right-hand corner, that in chaotic systems, there's this characteristic peak at late times, whereas in the non-chaotic spectrum, the peak is absent, and we can directly conclude this from the structure of the transition probability. Okay, so here there's actually a numerical plot of the transition probability.
Sorry, I have another question.
Yes.
So, so let's say you have an arbitrary Hilbert space, and you compute log complexity for that, and you observe this peak behavior.
Yeah.
Would you say that that system is chaotic?
Yes, exactly. That's the point we are making in the paper. So unlike at early times where we can't discriminate between chaotic and non-chaotic behavior, here at late times, the claim is that whenever there's a peak, then you have a chaotic system.
Okay, so in non-chaotic system, it won't be there, and it will only be there in the chaotic systems. And in every single chaotic system, it should be there according to your work, right?
Yeah, exactly. So I should say again that this was already conjectured in this paper by Vijay Balasubramanian and Saputa, Magan, and Wu. But here now, Joyu showed this both numerically and analytically explicitly that this is actually true. So I guess this is one of the main results of the paper that we have. Yeah. Yeah, thanks for the question. I hope this became clear.
So sorry, Johanna, can I just ask, is there some time scale that defines early and late?
Yes. Sorry, I know this is a very loose definition, but I think this is something which is kind of widely used in the literature, and so the time scale is that this dip here discriminates. So everything that happens before the dip is early, and everything that happens after the dip is late. Okay, so this ramp plateau behavior is the kind of late time, where this slope and behavior here is the early time behavior.
I see. And so because you can relate the second derivative of the average of the Krylov complexity to the spectral form factor, you can use that same time scale.
Exactly, precisely.
Okay.
Yes, thanks for asking. Yes, exactly. That's exactly what's happening. Yeah, thank you. Okay, so here so this is a numerical calculation of this schematic picture that I just showed again. So you have this dip and here, and then the ramp in the plateau. And so here, this is a numerical analysis for different values of this Krylov index n. Okay. Good. Any further questions? I mean, I don't know how much time I have. I would like to spend 5 minutes on this other type of project, because I think it's also very interesting. But maybe before I go there, let me just pause and ask if you have any further questions.
Actually, I do have one more question.
Yeah. Okay.
So since you had the Ehrenfest theorem for the Krylov complexity, right? And that's how you identify the relation between Krylov complexity and spectral form factor at early times.
Yes.
And you used thermofield double states to arrive at that.
Yes.
So my question is this sort of identification only valid for systems with double Hilbert spaces, or does it work for?
That's a very good question. I think it's valid more generally. I think so. We also I have to think we had looked at other examples. I mean, certainly we didn't just look, or I should say, Joyu didn't just calculate for the unitary ensemble, but we also looked at the SYK model, for instance. I don't know, Jo, are you around? Can you answer the question? Did we only look at TFD, or did we have other examples as well?
Yeah, my question. Yeah, of course, we also studied other model, but actually the so-called double copy here space here is just a trick for relating the spectral form factor to the Keylog complexity. So it means we start. You consider the TFD state as our initial state. So the Keylog complexity looks like here. But if you ask me, can we change the initial state? For some, we choose other state or random state, they will, in principle, they will give different result. Yeah. Then yeah. So
okay.
in this talk, we focus on the maximal entangle state or some predictable state. But yeah, but in our future world, we are further considering other state. Yeah, they will show slightly different behavior.
And if you have any like preliminary results, do you know if there is this identification still there between spectral form factor and Keylog complexity at early times?
Yeah. So can you repeat your question?
Yeah. So I'm asking, like, if you have any early results, is this identification still there between Keylog complexity and spectral form factor at early times? Is this dependent on taking TFT, or is it more generic? Do we have results?
Only taking TFT because spectral form factor is the survival amplitude of TFT state. If you change the state, the survival amplitude of that new state have nothing to do to the spectral form factor usually.
Right. Okay. Thank you.
Okay, excellent. Thanks for explaining. Okay, so for the last, thanks for you. So for the last 5 minutes, let me move on to this set of papers here. And okay, let me just because at the beginning I gave this motivation for me looking at Keylog complexity is also very much motivated by finding a gravity dual for complexity. And so this part of the talk has nothing to do with Keylog complexity, but it has to do with gravity duals of cost functions. And so coming back to the question of, if we can make these proposals of Susskind more precise. And let me just very briefly mention some of the aspects of this work that we had here, but I'll be extremely short about this. Okay, so here the idea is, if we want ADS-CFT, we should start with a CFT. And so there's this very nice work by Saputa and Magan where they propose to define a computational complexity in a two-dimensional conformal field theory by using the conformal transformations as being the gates. And then again, as in this Nielsen approach, one defines a unitary transformation using these conformal transformations as the gates. And then the reference state is usually some kind of primary state, and the target state is then obtained by applying conformal transformations. And then again, the idea is to define a cost function, which in this case is an expectation value of the gate with respect to this given state. In our initial, so in this paper and also in our initial paper on the topic, we looked at something which is actually just linear in the gates. But as I think it has turned out in the last couple of years, it's to actually get something meaningful, it's important to look at cost functions which are quadratic in the gates Q. Sorry. And for instance, one cost function that appears to be extremely useful is the so-called Fubini-Studi metric, which is quadratic in the gates, and in general it takes this form here where you can see there's two Qs appearing. So there's this nice set of papers by Florian and Heller, and so they were looking at conformal transformations that they expand in a small parameter epsilon. And to second order, they were actually able to show that this matches for the so-called Bagnanos geometries, which are kind of generalized asymptotically ADS spaces in 3 dimensions. This matches the complexity is equal to volume proposal. So that's actually very nice. And so we set out to go to higher orders or to prove this to all orders. But actually, it turns out that if you go to fourth order, then it's actually no longer true. And this relation is no longer satisfied in this expansion. So we had to come up with something else. And so what we've been looking at in constructing gravity duals for quantum circuits is to actually use the Pfefferman-Graham expansion for a particular conformal gate set. And so in fact, this case A is something that's been considered widely in literature, also by De Boer and collaborators, for instance. And so they look at time evolution and some external time parameter. So you have an ADS3 geometry with a time coordinate, and then you take a constant time slice in this geometry, and then you look at how this external time parameter evolves, and then compare to a system at a later time tau, which is given by this external parameter. But the idea of our work was to actually identify this external parameter and the actual time in your ADS3, asymptotically ADS3 space. And so we constructed the bulk geometry for conformal transformations of the boundary theory using the Pfefferman-Graham expansion. And so that's explained here. So then, I mean, we start here at some time with an ADS3 space, but then applying these different conformal transformations as a function of time, then our original ADS3 gets slightly distorted, so the black lines become the red lines. And so constructing the gravity dual for conformal transformations of the boundary theory. So okay, so our gate set looks again like this, and so now here is the idea is to identify this this gate with the actual physical Hamiltonian and the actual physical time. Okay, so obviously the Hamiltonian is related to the energy momentum tensor. So in a conformal field theory, this means for the boundary theory, this generates conformal transformations denoted by F here, and so the transformation of the boundary metric will do this for some particular time that we consider. And so what is nice in if we have an ADS3 space is that in this known number of dimensions, the Pfefferman-Graham expansion actually terminates at this order. So there's no more contributions after this fourth order term that we see here, G4. It's actually a second order term, but it's usually denoted by G4. And so that means we can actually reconstruct the entire metric of this new space by calculating the metrics at the boundary for this new after the conformal transformation. And so in that way, we can obtain a gravity dual for the Fubini-Studi metric, which at the boundary for the field theory takes this form. And it's a slightly involved calculation. And so in terms of geodesic, then at a constant time slice, as shown here, we find the gravity dual of this Fubini-Studi metric to take this particular form. It's slightly lengthy, but as you can see, it essentially involves metric components at the boundary. And also it involves derivatives of this geodesic length. Now, of course, we were hoping that our result would coincide with the volume written in this particular way. But the volume in this coordinate set actually only looks like this. And so this looks much simpler than, I mean, the terms look kind of similar, but in total, it's much more involved. So unfortunately, it's not so simple as to say it's just the volume. Nevertheless, what we actually managed to do is to find an explicit gravity dual of an explicit quantum circuit in this boundary conformal field theory. And I think this is a very nice step forward in this direction of making this proposal of Susskind much more explicit. So that's what I wanted to show to you at the end. Okay, but now I went for quite some time, and so let me conclude and ask for further questions. So in the largest part of the talk, we talked about the creed of complexity. And so as we saw, we obtain a relation between the Kirchhoff complexity and the spectral form factor via this transition probability in Kirchhoff space. And okay, maybe I should reiterate what Joyu explained. And so indeed, we looked at the thermophile double state, and for that case, this survival amplitude, so the amplitude for the particle not moving along the chain is actually equal to the spectral form factor. And for that reason, this relation works. And as Joyu pointed out, if we look at different systems, this relation is probably no longer true in general. But here in this case, this allows for analytical results, and in particular at late times allows for discrimination between chaotic and non-chaotic behavior. Okay, and then towards the end, in this other development, which is complementary but related, I showed to you that if we consider gravity duals for cost functions, then in this context of conformal field theories, we are able to explicitly construct gravity duals for the gates and cost functions of a CFT. And that certainly provides further insights into the relation between information geometry and ADS CFT, and is a basis for making further progress of making these Susskind proposals even more rigorous. Okay, so that's what I wanted to tell you about complexity. I hope you enjoyed the talk, and I'm certainly happy to take further questions. So thanks a lot.
Thank you very much, Johanna. That was a really great talk. Do we have any questions?
I think I have a question.
Yeah, sure, go ahead.
Right, Cameron, go ahead.
So you said the selection of quantum gates was sort of arbitrary, but then in part 2 of the talk, you just chose quantum gates and went and calculated, well, constructed this gravity dual. How do you know that that gravity dual has any meaning if the choices of gates is arbitrary?
Well, okay, I think my statement is that the gravity dual I'm construct is particularly adapted to my choice of gates. Okay, so okay, so okay. Yes, the choice is arbitrary, but I can make a particular choice. Okay. And the choice I make here is just that I choose my gates to be conformal transformations. Okay, so, and then I know that these conformal transformations are generated by the energy momentum tensor in a conformal field theory. Okay, so I think the answer to the question is there's a lot of arbitrariness, but I fix this by saying that I would like to consider a two-dimensional conformal field theory. And then I fix this by saying I would like my gates to be conformal transformations. Okay, of course, this is a totally arbitrary choice, but it's, I think, a meaningful choice if we look at a conformal field theory. Okay, and if we do that, then I can explicitly construct a gravity dual of these particular gates that I chose. Because there's several nice features, for instance, the Pfefferman-Graham expandable terminates in this low dimensional setup. And so everything falls nicely into place in such a way that I can, unfortunately, it's not quite the volume, but nevertheless, I get a geometrical object in the bulk, which I know is dual to what I started with the gates I chose. Okay. But you're absolutely right that this is just the beginning, because it's not all the transformations that are possible. And in fact, if I just take this particular gate, then it means I only look at gates that are kind of ladder operators inside one Werner module. Okay, so if I have one representation of the conformal group or algebra, I start with a particular highest weight state given by some weight 8. And these transformations, they will take me then, inside this one Werner module. But now assume, of course, there are many more transformations that are possible and which I didn't consider yet. For instance, if we go from one Werner module to the next Werner module, okay. This is actually something we study right now with Annalena and a master student. So if we add a scalar field to this, a primary which takes us from one Werner module to the next, how is this analysis going to change? And so the answer to the question is, for this particular choice, which I'm allowed to make to fix the arbitrariness, I can tell you what the gravity dual is, but it's not the most general set of gates that I can take in a conformal field theory. There are certainly others which I would like to include, and that we still have to work on. I hope that answers the question.
Yes, yes, thank you very much.
Yeah, thanks for asking.
So this map is not one-to-one though, right? I mean, I could pick another set of gates in the QFT and possibly end up with the same gravity dual, or do you know that?
Okay, yeah, that's an excellent question. I think that's probably motivated by your study of the Fisher information metric.
Right, yes, exactly.
Yeah, actually, I should also say, I mean, I very much enjoyed reading your papers together with Jonathan, also about the Fisher information metric, and you know, it's very nice to have this connection between, you know, a Gaussian distribution and the ADS geometries. But I mean, I think what I learned from your papers is that this is not unique, and yeah, so that's of course a bit disappointing.
Right, right.
And
Everything
here,
maps to ADS basically.
yeah, exactly. Yeah, it's a very good question. I mean, of course, it's more restrictive. Okay, this is a very good question, and I'm not sure I have an absolutely complete answer to this. However, I think here it's more constrained, okay, because I say I pick a particular set of conformal transformation and say those should define my gates, okay. And as I said in the answer to Cameron's question, I mean, it's I can imagine taking more gates, okay, but of course complexity always depends on, I mean, as long as we don't talk about field of complexity, I mean, it depends on the choice of gates. So, and if I just choose the gates that move me inside one Verma module, then this prescription is actually unique, and I think it works both ways. I mean, because I think via this equation, which is the Fefferman-Gray expansion, which terminates if I look at ADS3, then for any conformal transformation that I do at the boundary, which is generated by the Hamiltonian, of course, then isn't that the content of the Fefferman-Graham theorem that as long as the equation of motion is satisfied in the bulk, I can write down a metric in terms of the boundary metric.
Right, I think that's the case, right? So I was wondering if the HKLL story played any role in this here, because you're
yeah, that's a very good question.
Your data is prescribed on the boundary, and in some sense you're pulling that back to the bulk.
Yes, that's right. Yeah, that's right. You know, Jeff, it's an excellent question. I mean, the only thing I can say is it's a little more constrained than just looking at the Fisher information metric of a random quantum field theory.
Sure.
But okay, I'm not going as far as claiming it's unique, but okay, certainly what we have on top here is that, you know, we really have this Fefferman-Graham construction in this lower dimensional case, which I think is probably a little more restrictive. But if that's sufficient to eliminate any arbitrariness,
right. It feels like it shouldn't eliminate all the arbitrariness, but it's sufficiently constrained that I would imagine that you would land up in equivalence classes of bulk geometries.
yes.
That is to say, you can take some set of transformations in the boundary theory, and that'll map you to some class of geometries. And I guess it would be nice to classify that.
Yeah, exactly. Yeah, you're absolutely right. No, it's a very good question. Yeah. Okay, I will definitely think about this. It's a super interesting question, and I don't have a good answer.
I have another observation. I don't know whether this is relevant or not, but it's for me, it's particularly nice that you were able to relate the average of the Krylov complexity to the spectral form factor.
Yeah.
So my postdoc, who I think is still in the room, Jaco, wrote a paper. Jaco Franzel and Robert de Mello-Koch wrote a very nice paper some time ago, showing how you could get the at least for bosonic quantum mechanics, you could get the spectral form factor as an average of the OTOC over the Heisenberg group. So I wonder if there's a further link to be made relating the Krylov complexity and the OTOC.
Yes. Okay. Again, I think I need to ask Joyo about this. Joyo, you considered OTOC also in the paper, didn't you? Do you have any comment about this?
Yeah, first one question. I think for example, when you mentioned the relation between spectrum form factor and the OTOC, in that case, one should sum over all the possible operator, right? When you try to make the connection, because summing all the operator will give the replica. We try to we give some replica treatment for the OTOC, and then you may end up with the spectrum form factor. So I think if you ask, is there any relation to the Krylov complexity? I think maybe it relates to the Krylov complexity of all the random operator. For example, we start from an operator and start a Krylov complexity, and then we try to sum over all the possible operator, all the possible initial operator, and maybe take the average of that Krylov complexity. Maybe we can end up with something like something like the OTOC here.
I see. Okay, that's interesting.
Yeah. Actually, I think the better point model would be the spectrum complexity. In that case, it more looks close. It looks more like just like this. Yeah, it looks more like a spectral form factor, but with different weight. Yeah. Yeah. So yeah, one can insert operator there and then sum over all the operator, and maybe it looks like what you want. Yeah.
Great.
Yeah. That's
Excellent. Well, thank you.
well, yeah.
If there aren't any more questions, let's thank Johanna. That was an excellent talk. As you say, I really look forward to your next visit to Cape Town.
Yeah, thank you very much. Yeah, I would definitely like to come, but on a more immediate and simpler way. We also have a Zoom seminar here in Würzburg, and of course, it would be very nice if you could give a talk about your recent papers on Krylov complexity. And I'll talk to this. I mean, when are you in your? Is the term still going on, or do you have a?
Well, the term actually comes to an end next week.
Right. Okay.
Well, actually, no. The lectures are finished last week, and we've got exams coming up next week. Yeah. But I'm going to be in Europe actually over June, July. We're associates at ICTP, so we're spending. We typically spend a month at ICTP over June. But if you're in the neighborhood, I know. There's a couple of things happening at ICTP. I'm not sure if you were in them, but there's this black hole huddle that
I didn't know. Yeah, unfortunately, our term still goes on until the end of July.
Right, I know. I invited Rene, and he said no. Unfortunately,
exactly.
He has teaching, and that's.
Yeah. But so we have a seminar on Tuesday. So I mean, maybe I can just send you an email and.
Yeah, that would be nice.
I don't know on the top of my head when the next available slot is, but we should get in touch and you can give a Zoom talk about it.
Happy to. Thank you.
To organize, yeah.
Excellent. All right.
Yeah. Thank you very much.
Thanks so much.
I didn't see Jonathan, so if you see Jonathan, please say hello for me. And
I got a message from him saying that he's had student consultations
okay.
right up until 5 minutes ago or something.
Okay. I'm sure there will be.
Anyway, I'll pass your regards on.
Okay. Okay. Well,
Thanks,
for
Johanna.
the invitation. It was lovely, and let's keep in touch. Yeah. Thank you very much.
Excellent. Okay. Thanks.
Bye-bye.
Bye-bye.
Bye. Thanks.
Bye, everybody.